Here we go again, folks, and we are finishing up our unit on uh, atomic basics and nuclear chemistry, and we only have a couple concepts left, but I thought it might be a good idea here to give us a summary once again of nuclear chem. So here we have nuclear chem, right? We started off, and the first thing we wanted to do is say, hey, there's a difference between a chemical reaction and a nuclear reaction, right? We said the chemical reaction involves electrons and the nuclear reaction involves the nucleus, the changes to the nucleus. And then we said, hey, there's some nomenclature that we need to know. There's some things, some basic concepts that we need to know if we want to talk about nuclear chemistry. And we said we have this idea of a radioisotope. We said a radioisotope is essentially an element with an unstable nucleus, right? And anything above bismuth has an unstable nucleus. And then we talked about radioactivity, and we said that radioactivity is the spontaneous disintegration of an unstable nucleus. And then we talked about, well, I guess we should pull off here. We said radioactivity is the spontaneous disintegration of an unstable nucleus in which particles and or energy are emitted, right? And those particles and or energy is radiation, right? Radiation. And we talked about 4 types of radiation. We talked about alpha. And we said alpha was when the nucleus emits a helium nucleus. Beta. Beta is a case where I have a neutron that becomes a proton and an electron, and the electron is emitted. We had positron radiation, and that's a case where I have a proton that breaks down into a neutron plus a positron, and that positron is emitted, and my symbol for that was EU0 plus 1. And then we had gamma, right? And we said gamma is just the release of energy from my nucleus, and it does not lead to, what do we call that? A transformation, right? We said we can have transformations that because of radioactivity, we can have some transformations, not transformations, excuse me, transmutations, right? And when I have a transmutation, the element is changed to a new element, so one element becomes a new element, right? That means that number of protons must change. And what else? Oh, we also talked about, hey, what are some causes of radioactivity? What causes a nucleus to be unstable? And we talked about external causes. And those are things like bombardment and capture. Bombardment, like bombardment by a neutron, or capture of an electron, or capture of an alpha particle. And we said some causes can be internal, and that just means when nature made some of these, they were unstable. Why? Because they either have a high proton to neutron, proton to neutron ratio, or a high neutron to proton ratio. And we did say here, hey, internally, if you have an atomic number greater than or equal to, right? So greater than, how do I do greater than? There we go. Greater than or equal to 81, it is going to be unstable. Or at least it's going to be a radioisotope, right? Radioisotopes, right? If it's above bismuth, it's going to be a radioisotope. Good. What else? Well, I think that's just about all we've covered so far. And really, we have two more things we want to talk about. And I'm going to erase this here so I have a little bit of space. Good. Because it comes out of the idea of radioactivity, and I guess maybe I should come up here and say, no, we can also do one other thing. Maybe it's best if I say, hey, we can do nuclear equations, right? Nuclear equations, and that's where there's a mass balance between my mass numbers, right, and between my atomic numbers. So whenever I write a nuclear equation, I have to have my mass numbers equal. The reactant side has to equal the product side, and my atomic numbers have to equal each other. Good. And so I guess there's one other thing we need to talk about here. Well, really two. We want to talk here, when we talk about radioactivity, we want to talk about half-life. And we want to talk about, I guess I would call it two forms. Well, not really there. I guess I would take this off my nuclear chem. We need to bring this down this way. And we want to talk about two specific forms of nuclear reactions, or two types. And that's where we're going now. We want to talk about two types. One of them is called fission, and one is called fusion. Okay, so if we look at our next consider, here it is. Consider the following nuclear reactions. I've got hydrogen 2 plus hydrogen 3 yielding helium 5. We call hydrogen 2 deuterium. We call hydrogen 3 tritium, and it forms helium 5. And then consider uranium 235 capturing a proton, or be bombarded by a proton, bombarded by a neutron, and it makes tellurium 137 and zirconium 97 and creates two more neutrons. Which of these is fission, which is fusion? So we have to understand then what is fission and what is fusion. Good. Two types of nuclear equations. Fission is when I have a large, and that's a relative term, nucleus, which breaks down into smaller nuclei. Okay, so I have a bigger nucleus that breaks down into a smaller nucleus. Fusion's just the opposite. Fusion is smaller nuclei react with each other to form a larger nucleus. Okay, and fission is, examples would be kind of, for us, our nuclear power plants. Nuclear power is fission right now. It would be really nice if it were fusion, but unfortunately it's not. Fusion, hey, this is the sun and like the atomic bomb. Fat man and little boy, right? The atomic bombs were both fusion bombs. Not the atomic bombs. Sorry about that, folks. The hydrogen bomb. The hydrogen bomb. Teller's baby. The hydrogen bomb was fusion. Hey, my atomic bombs, Hiroshima and Hiroshima, were fission bombs. Great. So there we have it. Fission, you have a big nucleus breaking down into smaller nucleuses, nuclei, not nucleuses, and that is nuclear power, the atomic bombs, and fusion, two smaller nucleus that fuse together to make a bigger nucleus, and that's what's happening in our sun, and that's what happened with the hydrogen bomb. Okay, so let's analyze our consider. So what do I have going on in the first case? I have deuterium and tritium, hydrogen 2 and 3. Those are smaller nuclei, and they make it bigger. So what happens when I have smaller making it bigger? That is fusion, right? Good. In this case, I have a big nucleus, and what happens? It forms two smaller nuclei. This would be fission, the breaking up of my nucleus. All right? What can you do? Here you go. Take a look at this. You tell me what you think. Well, what do you notice? I have plutonium-239, and what do I make out of that? Cerium-144 and krypton-94. That means I have one nucleus going to form two nuclei. That is what? That is an example of fission. Okay, fission, fusion, piece of cake. Let's move on to the last concept. Here we go for the unit. I have 1.200 grams of uranium-238. The half-life of uranium-238 is 4.5 times 10 to the 9th years. Yow, that's a long time. How much of the uranium-238 remains after 4 half-lives? This looks kind of scary. I got some numbers here. Yep, and I have a big number there. That might scare me. And there's a new word, half-life. Oh boy, what is half-life? Well, let's go back to our notes. I did refer to that briefly. You can see here, half-life. Let us start off from half-life here, and let's learn a little bit about half-life. Half-life it's really a simple concept, folks. And you hardly need a calculator to do these when they are first order half-lives, and that's what they all are in honors chem or iChem. Half-life is a time, okay? Now, half-life, that's kind of the symbol. Half-life, it is the time it takes for 1/2 of a sample of a radioisotope to decay. That's it. The time it takes for 1/2 of a radioisotope to decay. Good. Now, let's think about some problems that I could do with this. Let's say, I'm just going to make up some numbers. Let's say I have a radioisotope X, and I have 10 grams of that. Good. What happens in a half-life? Well, let's say 1 half-life. Here it is. There's 1 half-life. What happens in 1 half-life? Well, a half-life is what? The time it takes, the time it takes for half of the sample to decay. So if I start off with 10 grams, after 1 half-life, what happens? Half of that decays, meaning after 1 half-life, I have 5 grams. Good. How long then does it take for me to get to 2.5 grams? Well, it takes another half-life. How long does it take then for it to go to 1.25 grams? Well, it takes another half-life. You guys getting the idea? Each half-life reduces my amount by 2. I mean, divided it by 2, reduces it by 50%. So let's take a question. Let's say I have 10 grams of something, and the half-life is equal to 2 days. Got it? How long until I have 1.25 grams? Well, in 1 half-life, I have 5 grams, right? So that's 1 half-life. In my second half-life, that's divided again by 2, right? So I get 2.5 grams. In my third half-life, I get 1.25. Notice I've just taken my 10 divided by 2, my 5 divided by 2, my 2.5 divided by 2, and each of those is a half-life. So how many half-lives does it take to go from 10 grams down to 1.25 grams? 1, 2, 3 half-lives, right? Each half-life is 2 days. So I have 3 times 2 days And what's my answer? 6 days. That's it. That's how easy half-lives are. Okay? Good. Let's see what you can do. Let's do this first one together, and then we'll see what you can do on your own. How much of my uranium-238 remains after 4 half-lives? What do I start with? I start with 1.200 grams, right? So after 1 half-life, T1 half, right? After 1 half-life, what's left? 0.6000 grams, right? After a second half-life, what's left? 0.3000 grams. After a third half-life, what's left? I divide that again by 2. 0.1500 grams. And after my fourth half-life, how much is left? We've got to divide 15 by 0.1500 by 2, 0.07500 grams. I believe that is the correct answer, right? There we go. How much of the uranium-238 remains after 4 half-lives? Let's make sure I don't want to mess up my division, but I think I did that right. Yep, good. Now, let's look at the second question. How many years does it take to reach this amount? Well, that's a piece of cake. I have 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So I have 4 half-lives, and each half-life is how long? Each half-life is 4.5 times 10 to the 9th. 4.5 times 10 to the 9th years. And so I do that multiplication. 4 times 5 is 20. Carry the 2. 4 times 4 is 16, 18 times 10 to the 9th year. So 18.0 times 10 to the 9th, or 1.8. I can only have 2 sig figs here, can't I? So we're going to have to get rid of that 0. So 1.8 times 10 to the 10th years. Sounds good? That's my answer. You guys try this one. Put me on pause, and when you have the answer, unpause me. Well, did you have any problems with this? I hope not. Just go ahead and don't try to do anything complicated. Make it simple, right? We start off with 0.2400 grams. I have 6 half-lives. Okay, so that means 1 half-life, and after 1 half-life I have 0.1200 grams. 2 half-lives, 0.06000 grams. 3 half-lives, 0.03000 grams. 4 half-lives, 0.01500 grams. 1, 2, 3, 4, 5 half-lives, 0.00750 grams. And let's make sure, I don't want to screw this up. Divided by 2, yes, I can still divide by 2 in my head. Divided by 2, just to be safe, 0.003750 grams. How much? I believe my answer is this. 3.750 times 10 to the what? 1, 2, 3 times 10 to the minus third grams remain, if I do that in scientific notation. How many years does it take? Well, we had what? 6 half-lives? 1, 2, 3, 4, 5, 6. I had 6 half-lives, and each half-life is how long? 4.5 times 10 to the 9th years. So that looks like what? 24 and 3, 27. So 27 times 10 to the 9th, or 2.7 times 10 to the 10th years. Does that make sense? 6 times 4.5 times 10 to the ninth. And sure does. Looks like a winner to me. Good. Next type of half-life question. Okay, we have 0.7248 grams of cobalt-60, and it tells me I have 0.04530 remaining after 21 years. What is the half-life? Okay, here's the way I work this kind of problem. I have a starting amount, and I have an ending amount, and I have a total number of years. So, here we go. This is my total years. I have 21.2 years, right? Good. Now, what do I start with? 0.7248 grams. First thing I want to do is divide this into 2, right? So when I divide this by 2, that's 1 half-life. So here's 1 half-life. So I have 0.7248, divide that by 2, and I get 0.3624 grams. Is that what I want? No. So let's divide that by 2. So that's going to be another half-life, right? So divide that by 2. So divide that by 2, and what do I get? I get 0.1812 grams. Is that what I want? No, it's not. So what do I have to do? Divide that by 2. That's another half-life. So I divide that by 2, and I get 0.09060 grams. Is that what I want? No, I want 0.4530. So I have to divide that by 2. And when I divide that by 2, and what do you think I get? I get 0.04530. Woohoo! That's what I want. So how many half-lives did it take me to go from here to here? Well, there's 1, 2, 3, 4. So it took 4 half-lives. Now, that means what? 21.2 years equals 4 half-lives, right? So what does 1 half-life equal? Well, what am I going to do? I'm going to divide both sides by 4. Since it takes 4 half-lives to get 21.2 years, then 1 half-life is 21.2 years divided by 4. Yoink! 5.30 years. Good, good. Hey, just off to the side, why do I have 3 sig figs here when I have only 1 sig for this 4? Well, this 4 is a count. 1, 2, 3, 4, 5. It's a count, and counts have infinite sig figs. They are not measurements, so they don't affect our significant figures. Since I have 3 sig figs here, and I divide by a count of 4, I need to have 3 sig figs in my answer. So 5.3 years. Here we go. You do the last one of the unit. This is it. Put me on pause. Well, you get it? We start off with 2.424 grams, and they tell me how much remains at the end, and that the total is what? 11.47 days. Good. So what am I going to do? I divide by 2 here, and that'll give me my first, after 1 half-life, 2.424 divided by 2 gives me 1.212 grams. That's 1 half-life, right? Another half-life. Divide that by 2. 0.606 grams. Oh, sorry, folks. Excuse me. And divide that by 2. I know that had to sound really nice, but I get 0.3030 grams after that half-life. Is that what I want? Hey, that's what I want. Look at. Woohoo! Good. How many half-lives did that take? 1, 2, 3. It takes 3 half-lives, 3 T1 halves to go from 2.424 grams to 0.303 grams. And that total is equal to my 11.47, right? So I have 3 half-lives equal 11.47. So what does 1 half-life equal? Well, 11.47 divided by 3, and I get, not that right, that's completely wrong. 11.47 divided by 3, and I get, how about 3.823 days. That's it. I hope you all can handle this. Give it some practice, do the homework, and then you're ready for the quiz. And you are now nuclear chem experts. Ciao.